Okay, we are still chapter 14. And we got into sort of the second part of chapter 14 last time, and we talked about the common ion effect. And that is really a situation that you have with really the main topic that we talked about, which was buffers. And a common ion effect is what the name it sounds like. You have some type of ion present that is in common. Say it like that guy. And that causes the equilibrium to shift away from it. And what it essentially will do, for example, in a weak acid or a weak base, is it will basically keep it together. So it will prevent really the weak acid from breaking apart and producing more H plus. It will also prevent really the weak base from sort of producing more OH minus because it's going to keep both of the weak base and the weak acid together due to the common ions presence. Now, when we have common ion problems, which really are buffer problems, we could use an ice table like normal to solve it. It is important that if you are doing a ice table to solve these type of problems, like we talked about, you should probably have some molarity here. You might not have anything there, but you also should have some molarity on both sides, right? So because of the common ion being present, you will have an initial concentration of both either the weak acid or weak base, and also his conjugate partner on the other side. And again, that is very commonly missed when people sort of do the ice table part of it. They sort of miss that guy. So like the example, if we had acetic acid and acetate, we should have an initial concentration of this guy 0, and again, an initial concentration of that guy. And if you don't do that, like we talked about last time, you're essentially just doing the weak acid problem again, and you will not get obviously the right answer. The other mistake that people make is sort of when it comes to the change part, they're so used to it being minus X that they forget that it's actually plus X as well. So those are two things you do want to watch out for if you take the ice table approach. What we actually saw when we did, for example, a problem with the ice table is because of the common ion effect, in this case, if we had sodium acetate involved, pushing the equilibrium back the other way, we actually get a really small amount of change that occurs. And because of that, what happens is sort of the initial concentration of like the weak acid and conjugate base and the final concentrations of the weak acid and conjugate base will essentially be the same. So they don't really change all that much. And because they don't really change all that much, we could avoid in these situations sort of the ice table if you wanted to, and you could use the Henderson-Hasselbalch equation, which is commonly used for buffer situations, where the pH is equal to the pKa plus the log of the base over the acid. Remember, the pKa value is minus the log of the Ka. There is, again, also a sort of basic version of this equation, but it is a little bit different. It does use the pKb, and it is acid over base, where the pKb is equal to minus the log of the Kb. As I mentioned before, although some people will use sort of this equation, I personally think you should always just go into this equation because probably 9 times out of 10, or even more than that, you're going to be asked for the pH anyway. So you might as well just calculate the pH directly without having to go here, which only gets you the POH, and then still has to subtract 14. So you could use the Henderson-Hasselbalch equation for any situation, acidic, basic, neutral, it doesn't matter. You could always go into it as long as you have the base on top, acid on the bottom, and you're using the pKa value. You could always use it. Again, it doesn't really matter if it's acidic or basic. But there is a nice relationship we talked about between the pKa and the pKb value, which means if you add them together, it does equal 14. So that's sometimes helpful as well, in case depending on sort of the value that you have given to you. If you want to use the Henderson-Hasselbalch equation, you have just the Kb value, you get the pKb, and subtract 14, get the pKa really easily, and get there to what you need. Now, we talked about buffers, I think, last time to really finish it up on. And remember, a buffer is basically made up of a combination of two things. It could either be a weak acid and the salt of its conjugate base, like acetic acid and sodium acetate, which would be a salt of its conjugate base. The sodium there is what makes it a salt. It's an ionic compound. It has some type of spectator ion, not really doing much, but just hanging out there to balance out the charges. Or you could have a weak base and the salt of its conjugate acid, like NH3 and NH4 plus. So that again is a weak base in its conjugate acid or conjugate acid pair. Remember that having both of those parts in the solution to start with is really what makes a buffer effective, because essentially if you took the acetic acid example, you have in that solution an acid part to your buffer. You also have a base part to your buffer. And that works really well, again, when you drop in something like an acid into your buffer. The acid will basically be a source of H plus and Cl minus. That H plus, when it comes in, will actually react with the acetate. And the result of that is it will actually make more of the acetic acid in that particular case. The result of that is you make acetic acid, which is part of the buffer. It doesn't affect really the buffer or the pH because of that. And really what it's doing is it's preventing that free H plus from just floating around freely. It gets tied up really with the acetate there to make acetic acid. And because that H plus doesn't go into the solution as more H plus, really the H plus concentration you started with is relatively constant. And that's what keeps the pH relatively constant as well. Same thing happens again if you sort of dumped in your base into this sort of buffer situation here. And if you did a little sodium hydroxide, for example, that's going to basically be some sodium ions and hydroxide ions going for a swim. And really in this case, what sort of prevents, you know, that hydroxide is it's going to basically react with, well, it's going to really react with, I guess, the acetic acid, and it will ultimately form some water, basically, in that case. And the hydroxide coming in reacts with the acetic acid, forming water. Water obviously is not going to affect the pH, also is going to keep the H plus concentration relatively constant. So basically how a buffer works, because it does have a acid part and a base part, when you add additional acid or base to it, it's able to prevent the formation of free H plus in the solution and able to prevent the formation of free OH minus in the solution when you add a base. And both of those things, because H plus and OH minus concentration are related to each other, what that's able to do is not add any more of that, and that keeps basically the H plus concentration relatively constant, and also will keep your pH constant. So remember that you sort of you have acid part, base part of your buffer. When you add acid, it will react with the base, but it will generate more of the acid part of your buffer. And when you add base, it will react with the acid part and make the other part of the buffer, which is the base part of the buffer in that case. So it sort of regenerates half of the buffer when you use it and you add acid or base to it. And there is buffer capacity, as we talked about, that you can blow right through a buffer if you add the wrong sort of concentration of acid or base to your buffer, or you just keep obviously adding acid or base. Lastly, we talked about that you could use the Henderson-Hasselbalch equation to help you decide what you should make your buffer out of. So an effective buffer has a pretty good concentration of both acid and base components. And if you keep those about the same concentration, that will basically turn this into the log of 1, which is 0. And basically, you would want to select a weak acid or weak base that has a pKa value or plus or minus 1 of your sort of desired pH. So whatever you want to make the pH of, you want to find a weak acid or weak base that has, a pKa value pretty much in that ballpark. The closer the better usually. And that is how you would choose, what you want to sort of make it out of. Any questions on any of that stuff there we talked about there? The reason as well that you cannot have a buffer out of a strong acid or a strong base is why can you not have basically a buffer that's made up of a strong acid or strong base? What happens with a strong acid or strong base when it goes for a swim? Stay together or completely break apart? Completely breaks apart, right? So let's just say you wanted to make a buffer out of hydrochloric acid and like sodium chloride, and you're like, well, they are related to each other. That's HCl and that's Cl minus, right? So that's like an acid and its conjugate base, barely, right? Problem is when you go throw those guys into the pool here for a swim, they're both going to actually break apart. Nobody's going to set up an equilibrium. So you're just going to get H plus, Cl minus, and Na plus, and Cl minus. And really, you don't have an acid part to work as an effective buffer. You basically just have H plus floating around, which is going to change the pH, obviously, of that solution. And you have a conjugate base part, but you have no acid part. There's no way for that acid part to stay in the solution. That's why when you do like a weak acid, and its conjugate base. When you put that into solution, because you have a weak acid, that is able to basically keep both parts of the buffer in the solution. It will have an acetic acid part, it will have an acetate part, and by adding the sodium acetate, you kind of beef up the acetate part as well. So you have a good concentration of both of those guys still floating around in that solution. Again, with a strong acid or strong base, if you try to make a buffer strictly out of that, you will only really have one component of a buffer. You'll either have like the acid part of the buffer or the base part of the buffer. You won't have both. And the problem with that is if you continue to add HCl in here, you're now going to get a buildup of H plus happening, and you're going to obviously see a pretty big jump in the pH, which is why it's not a buffer. So a buffer cannot be made up of a strong acid or strong base for that reason. It was not able to keep both components of a buffer in solution because it's just going to completely break apart and actually going to do the opposite effect. It's actually going to increase the amount of H plus or OH minus if you try to do it with a strong acid or strong base. Any questions on that there? With that being said, you actually can make a buffer out of a reaction of a strong acid and a strong acid and a weak base, or a strong base and a weak acid. The deal is, though, the buffer is not the strong acid, strong base in that scenario. It is completely gone. It's the result of that reaction will actually make a buffer. So it's not actually the strong acid or strong base doing it. It's just the result of the products that you get. And we'll see that a little bit later on as we go through this chapter. So let's talk a little bit here about that. Obviously, in a buffer solution, we're going to get that pH basically remaining relatively constant. As we talked about last time, if you're monitoring the pH, you definitely will see some changes in the pH, but you will not see drastic jumps in the pH. It'll go up a little, go down a little bit, which is also good if you're doing calculations. You should know if you have a little bit of acid, the pH should go down a little bit. If you have some base, the pH should go up a little bit, but again, shouldn't jump. Here in a non-buffer, like we talked about with water, because of that high influx of H plus, for example, right off the bat, we're going to see a pretty big drop in the pH, say from 7 there, all the way down to like 2. And that's because, again, it does not have the buffer capacity to handle that H pluses coming in. All right, so take a moment. Which one of these would... Okay, so let's take a look. So the first couple of things we want to figure out is, first off, are they related to each other? So obviously here we have KF and HF. That is basically K plus and F minus, which means these two guys are basically related to each other by an H plus. The other thing we need to make sure of is HF is what type of acid? That is a weak acid, right? It's not one of those 6 that we saw that is strong. And that would then be his conjugate base. And this would be the salt of his conjugate base because it has a potassium there, basically. And that means that this guy would be a buffer in that case, right? Now, if we look at B, we have KBr, which is a salt. We have HBr, which is an acid. Again, that's K plus and Br minus, that's a salt. These two guys are related to each other. The only difference really is an H plus. Is this a buffer, though? HBr is what type of acid? It is a strong acid, right? That automatically eliminates its possibility because it will not be able to set up that equilibrium, so it will not be a buffer. So again, those are the two things you really want to look at. Are they related to each other by 1 H plus difference, the sort of Bronsted-Lowry definition, but you also need to make sure you got a weak acid or a weak base obviously involved in that. Here we got a little sodium carbonate and a little sodium bicarbonate. In this case, we actually get rid of the sodiums here. We basically have carbonate. And on this side, we have bicarbonate. Again, the difference here is 1H plus. That also originated from carbonic acid, which is not one of those 6, which means it probably came from something weak. And that would be a buffer. So it looks like A and C here would be buffers. B would not. Any questions on that there? All right, so now that we sort of hopefully understand buffers, what makes up buffers, how buffers function, let's do some calculations here involving that situation here, buffers. So once you start with A, we want to calculate the pH of a buffer that contains 1 molar acetic acid and 1 molar sodium acetate. The Ka value for acetic acid there is on the bottom, 1.8 times 10 to the minus 5. Let's see what you come up for. Okay, so let's take a look at this one here. First off, if they weren't nice enough to tell you it's a buffer, which a lot of times the problem is they will not tell you it's a buffer, you hopefully should be able to recognize that again, we have obviously here acetic acid, which is a weak acid, and I know that because it's not one of those 6, but also I got a Ka value here for it. And this is basically sodium acetate, which if you get rid of the salt part of it, the sodium is basically acetate. So again, these two things, basically the only difference is 1H plus, and that should tell you you're really in a buffer situation at that point. Again, a lot of problems won't really kind of tell you that. So you need to be able to kind of recognize that that's the situation happening. So in this case here, we basically got 1 molar acetic acid, which as I mentioned before is our weak acid. And we got 1 molar sodium acetate, which is our conjugate base, basically. And also the common ion sort of thing in this situation. And we have a Ka value here, 1.8 times 10 to the minus 5. So again, if you could recognize that it is obviously a buffer situation that's happening because these two are related, you can go right into the Henderson-Hasselbalch equation. You could calculate your pKa value here by taking minus the log of the Ka. That's going to be negative log of 1.8 times 10 to the minus 5. Going to give us a 4.74 for our pKa value. Popping that in here gets you 4.74 plus the log. Again, we know that that is our acid, so that's going to go on the bottom. Up here on top will go 1. That's going to give us a 0 and a pH basically of 4.74 at this point. Now, if you went ice table approach, which is perfectly fine if you wanted to do the ice table approach, you would use the acetic acid to set it up and just do a normal acetic acid breaking apart into H plus and acetate. And again, here we would have an initial 1 molar. This would be 0. And the important part here is you also again have from this guy that 1 molar. So you got to have it on that side. The rest of the table, minus x plus x plus x, equilibrium 1 minus x, x, and 1 again plus x on this side. Obviously into the Ka expression, solve for x, which will equal your H plus concentration into the pH, and you will eventually get back to the pH over there. So again, if you want to do ice table, you still can, as we talked about, but just make sure you do have the initial concentration over there on the right. Any questions on any of that there? All right, so now that we have a buffer, we want to perhaps know what would happen if we did add some acid or base to our buffer, right? So a really important concept in this chapter, the second half of this chapter and beyond, is this concept, which is if I take something like a buffer and I have a certain molarity of everybody floating around, and I take some acid or base and I add it in, which has its molarity. When I add the volumes together, does the molarity stay the same or does it change? Molarity is moles of solute per liter of solution, which means if you add more volume, should the molarity stay the same or change? Should change. Molarity will continue to change, right? Because when you do molarity, moles of solute, liters of solution, if you add more volume, that is constantly changing as you add volume, which means the molarity is also constantly changing. So when we add volume to another solution, or more volume to volume, if you will, like what we would do in a buffer where we would add acid or base to our buffer, we cannot do our calculations with molarity because it's constantly changing. The one thing that doesn't change is the top part, which is the moles of the solute. That is actually what the buffer is the moles of the solute, the acetic acid floating around in there and the acetate ions floating around. That is really what is acting as the buffer and reacting. So whenever you're doing this situation where you have a buffer, you're going to add acid or base to it, or much also comes about, as we will see shortly in this chapter, when we do titrations, because all we're doing is continuously adding volume, right? So as you add your titration from your burette, the volume keeps changing and the molarity keeps changing. You will do pretty much the same calculation, except that your first ice table will actually be in moles rather than molarity. So we will want to do this like in moles and not molarity when we add volume. We will also need an ice table to figure out what happened to the buffer. How did it change as a result, for example, of us adding acid or base to it? So let's take a look at part B here, where we're going to do that, and we'll go through it together so I can kind of show you what's going on. So what we want to know in B here is, using the same buffer, we want to know what will be the pH after we add 0.1 molar HCl. Now, in this particular problem, which is not the case in most problems, we're just going to assume that everybody's volume is 1 liter, just so we can focus on the calculation part. You don't always do that, so sometimes you do need to figure out, in most cases, you got to take the volume into account of the buffer and also the volume of what you're adding. So in this case, we're going to have our 1 molar acetic acid. We're going to have our 1 molar sodium acetate. And to that, we're going to add 0.1 molar HCl. We're just going to assume, once again, in this problem, not always the case for sure, that all volumes will stay at 1 liter. So we're just going to kind of keep the volumes constant. So the first thing that's going to happen in this case is we obviously are going to set up the reaction that's going to happen. So obviously here, this is my buffer. And when I add HCl to my buffer, which is an acid, will it react with the acetic acid part or the sodium acetate part? Should react with which part? Which part is the base part of the buffer? Well, I'm assuming it's not the one that says acetic acid. So it's going to be the sodium acetate, right? Will be the base part of the buffer. So when I add that to this HCl should react with the sodium acetate, which is the base part of the buffer. So again, what we got going on is we have our acetic acid that's going to set up that equilibrium. We're going to help it along by adding some sodium acetate, which is going to beef it up. When I dump my HCl in, I got H plus and Cl minus. When I do this, this is going to then go and react basically with our acetate. So the reaction that we will get is our HCl will react with our sodium acetate in this case, doing basically a double displacement reaction, positive, negative, gonna switch partners that way. And we'll make some sodium acetate, which is part of the buffer, and our sodium chloride in this case, right? Any questions on that reaction there? Remember that you always make the other part of the buffer that's not reacting, basically, based on what is reacting. Now, in this case, we do need to see what happened to our buffers. So this is going to need to be done in moles. So we'll take our HCl, and again, we're going to assume that it is constant volume of 1 liter. So that would give us 0.1 moles. Our sodium acetate here would then be 1 mole, as we take 1 molar times 1 liter. And also important, right, when you do this table, also missed by people, is it's not a buffer until I put my other part on there as well, that we also have 1 mole up, right? Any questions on that? So really important, obviously, like we talked about, this is your buffer. You do need an initial moles of each of those things. All right, so the change here is actually not going to be an X because, frankly, we know what should happen in this case. When I add the HCl to the buffer, should I have any HCl left afterwards if this is a good buffer? The purpose of the buffer is to basically use up all the HCl, right? So that's going to be the actual change part. It's going to actually be a number in this case. And it's going to be this guy. It is really the limiting reagent in this case, if you want to think about it that way, right? You have 1 mole of sodium acetate, 0.1 mole of that guy, and we're going to do plus 0.1 moles. That means when we reach equilibrium, we will have 0 of this guy, which is what we expect because it's a buffer. It should basically use up all that additional acid you put it in. We'll end up with 0.9 moles, I hope, of this guy, and 1.1 moles of this guy. First off, any questions on that ice table? So I would say that a majority of the time, if you're going to do an ice table where there are moles, you typically will have an actual number for the change part, not an X. Yeah. Any questions on that? So this table, and again, we kept the volume constant at 1 liter, which is not always the case. So you would have to use the liters in most cases of the buffer and the molarity and the liters of the acid HCl and its molarity to figure out the moles. After you do this first ice table, you should convert back to molarity. It is probably the best move that you could do for yourself because in a lot of cases, you will actually need molarity to continue on with the calculation you want to do. So if you still have it in moles, you're going to probably get the wrong answer. So in this case, again, keeping all the volumes at 1 liter, we'll divide everybody by 1 liter, and that's going to give us 0.9 molar, right? And here, 1.1 molar. Now, a couple questions. First question is, I sort of ignored the sodium chloride. Why did I ignore sodium chloride? It doesn't change the pH because it's a neutral salt, as you were just going to finish that sentence there. That is a neutral salt, right? So it's not going to affect the pH. So my practice, why put numbers there that you might want to use incorrectly later on? So if you know it's not going to really affect it, just kind of leave it alone there in the ice table. You don't really need it. Now, the second thing here is if at this point you still don't know what's going on or what you have going on, the ice table itself can help you decide what you still have going on. And what I mean by that is if I look at the ice table and I write the equation better than I did before, which means this should really be acetic acid, right? Thank you for not catching that. So I'll catch that right now. That should be acetic acid, by the way. Otherwise, I'd made a weird equation there. So when my H goes over to the acetate, it makes acetic acid. So what we have going on at this point is we could use our ice table to help us. And if we look and see, what we have left is acetic acid and our sodium acetate, which is still a buffer. So you could use your ice table to kind of help you decide where you're at this point. We are still in a buffer situation now that I got the right guy up there. And what that means is you really have two options at this point. We can go definitely back into the Henderson-Hasselbalch equation, or we could do an ice table again and use acetic acid and basically do the ice table with initial concentration on both sides. I'm gonna Henderson-Hasselbalch here. That means our pKa value is still the same, 4.74, because it's based off of acetic acid, plus the log here of our base, which should be this guy, 0.9, divided by our acid that I now have written up there, which is good, 1.1. And that's going to get us here a pH of 4.65. Again, if you did the ice table, you would have set up your acetic acid equilibrium. And again, at this point, what you would actually do is your equilibrium line here would become your initial line. So you just take those guys down, both of them down, obviously, and carry it across there. Any questions on that? So did our buffer work pretty good or not? So we started with a pH of 4.74, right? And we added some HCl to it, and it dropped down to 4.65, not a huge change, but it did change in the correct direction, right? Since we added acid, we would expect the pH to go down a little, and it did. So if you did this calculation and you ended up with a pH above 4.74, you're moving in the wrong direction because you added acid, right, and not base to it. Any questions on that there? So let's say, for example, to illustrate the idea of what would happen if we took this same buffer here and obviously our same Ka value. And we were going to add our 0.1 molar sodium hydroxide, right? And in this case, we're going to still keep everybody, all volumes at 1 liter, just to make it easier for the numbers. In this case, when we add the sodium hydroxide, which is a base to our buffer, it is going to react with the acid part in this case. And we will need to do an ice table to see what happened. So we will write our equation. I'm going to try to do better than I did on the last one here. So we should have a little acetic acid plus some sodium hydroxide. And again, we're going to produce some sodium acetate in our double displacement reaction. And we're actually going to get a little bit of water happening in this case as basically these guys switch partners like so. So initially here, we are going to convert our molarity into moles because we are adding volume, obviously, in this case. So when we do that, we will have 1 moles of our acetic acid. We will have 0.1 mole of our sodium hydroxide, and we will have 1 mole of our acid, sodium acetate in this case. Change here is going to be our base that we're adding. So people always screw this up sometimes, but it should always be the smaller number, right? So you don't get a negative, right? So your head is going to tell you not to take the smaller number at some point in this chapter. Always take the smaller number. Yeah, so always take the smaller number when you're doing the change part. Even if your head says, I shouldn't do it, trust me when I tell you, you should. So always do that. So we're going to subtract that. We're going to add it to this side. We're going to go into our equilibrium. Here we'll get our 0.9 moles. We will use up, obviously, here all of our sodium hydroxide. We'll have our 1.1 moles of our sodium acetate. Once again, at this point, after we do our ice table, we're going to convert it back into molarity. And again, we're just keeping our volume constant here to do so. Once again, if we look at what we got going on, we have our sodium acetate, we have our acetic acid still there at the end, and that is obviously still a buffer, which means we can then go into this and figure out what we got going on. So same pKa value, 4.74 plus the log. The one that's our base has 1 less hydrogen and usually a spectator ion. So that's going to be 1.1 divided by 0.9. And that's going to give us here a pH of 4.83. Did our buffer work okay for the base part? It did, right? Because again, we started at 4.74. Here we added base and it went up, which it should because we added base and it went up to 4.83. So again, you will see a slight change in the pH depending on what you add, but you shouldn't see a big jump in the pH if it's a good buffer. Question on that calculation there. Now, if you screwed up the reaction and screwed up the calculation and you ended up with that on your first calculation, it shouldn't have made sense because it was HCl. So again, you just want to make sure you think about your answer to make sure that it does make sense. Any questions on that there? Now, lastly here to show you what would happen if you made a real mistake, say in class or something like that. Let's take a look at what would happen to this situation and why there is something known as buffer capacity. Again, we're rolling with our same buffer example here. And we're going to add 0.1 molar HCl, and we have our Ka 1.8 times 10 to the minus 5. We're still going to keep all of our volumes at 1 liter constant. The mistake here would be maybe you didn't grab the 0.1 bottle and you grabbed the 18 molar bottle instead because it looks like 0.1, I suppose. Can't be that big of a difference. So you decide to add 18 molar HCl to this poor buffer over here. And we're still going to get a reaction in this case of our HCl, and it's going to react now with our base. So we'll take our HCl reaction. It's going to react with our, wow, I'm having a bang up day here with this one today, huh? One of these should be sodium acetate. There we go. There you go. I guess it's good I catch these errors, I suppose, right? All right, so we can get our reaction. Dare I try it again? Here we go. There we go. Do that. A little acetic acid and sodium chloride in this case. Thank goodness here. All right. One of those days. All right, so initially now we're keeping, again, all of our volumes at 1 liter. So that would mean I have 18 moles now of HCl. I have 1 mole of sodium acetate, and I have 1 mole of acetic acid in this particular case. The change in this case is going to be what thing at this point? It's actually going to be this guy. This is now my limiting reagent by a mile. This is now like my excess reagent, right? So the change part here is actually going to be minus 1 mole, and plus 1 mole. That's going to give me here something like 17 moles of HCl. It tried. 0 of that, and like 2 moles of this guy. I can again convert this back into molarity at this point by taking my 1 liter. What I have left at this point is acetic acid and hydrochloric acid. Is this a buffer? This is not a buffer. This is actually 2 acids, right? You just blew through your buffer, right? Your poor buffer only had 1 mole of buffer action, and you dropped in there 18 moles, and it could not handle it. You blew right through it. You now have a strong acid, which is basically just littering your solution now with H pluses all over the place, right? And to add to that, you have this weak acid is going to break apart a little and add a little H plus itself. Your pH just went way down. Yeah, you just had a giant jump in pH because you basically just blew through your buffer. So that's why it's important what we were talking about the other day, that when you make a buffer, you got to think about really the moles of the weak acid conjugate base or weak base conjugate acids you have for the buffer, and like the moles of the acid or base you're going to bring in, and make sure that you have enough to handle it. And if you don't, you could run into this situation where you basically blow right through a buffer. Extreme situation in this case, but you know, or you grabbed the wrong bottle or something like that. Any questions on how to do these calculations or sort of buffer capacity there? All right, we're laid up there for today, I think.